All right, believe it or not, here we are, the last section in Chapter 7 on gases. So we've covered quite a bit of ground, and we have just one last idea here with gases left. Hopefully you found the gas law chapter to be fairly comfortable, and you're getting used to the math that goes behind these various laws. So our last gas law, Dalton's law here, deals with partial pressure of gases. So we've already discussed the idea that gases act like hard spheres, billiard balls, if you will, and they don't really know much about each other. But the one thing that you do see with gases is that the individual gases exert their pressure in order to get the overall pressure. Gases mix in all amounts because there's so much space in between them. So a mixture like air, which is mostly nitrogen, and then oxygen and lots of smaller amounts of other gases, there's partial pressures. Some of the pressures due to the nitrogen, actually roughly 80% of it's due to the nitrogen, and then roughly 20% to the oxygen, and then smaller partial pressures due to the other components. So each gas exerts its own pressure and gives rise to the total pressure by contributing its partial pressure. All right, so there you have it, just like we've covered in a gas mixture. Each gas exerts its partial pressure, which is the pressure it would exert if it were the only gas present in the container. So if we have a pure sample, a sample that is just one type of gas, then the total pressure is the partial pressure of that gas because there's no other gas to consider. However, since we often have mixtures of gases, Dalton's law helps us to understand the total pressure as being due to the sum of those individual pressures. And if we know the total pressure and we know the partial pressures of some components, we could solve for the partial pressure of the missing component, for instance, or likewise, if we knew the individual partial pressures, we could sum them together to find the total pressure. So we have a fair deal of information that we can glean by applying Dalton's law here. And of course, as you know, we're likely to have to solve some problems together soon. But before we dive into difficult problems like we have in the past, let's start with something simple, a very visual problem that we have here, where we have one cylinder that has a partial pressure of helium that's 2.0 atmospheres, and then we have a neighboring cylinder with argon having a pressure of 4.0 atmospheres. If we were able to allow these two cylinders to combine gases while retaining their volume, then what we'd find is that that total pressure that we arrive at would be a total of 6.0 atmospheres, the 2.0 atmospheres from the partial pressure due to helium plus the 4.0 atmospheres from the partial pressure due to argon. So it's not terribly difficult. Of course, it's going to probably be a little messier, mathematically speaking, than this simplified example, but the core concept is the same. However, many gases you have, each is going to exert a partial pressure to give a total pressure of the container. Now, if we think back to our molar volume, if we have STP, standard temperature and pressure conditions, 1 mole of a pure gas will exert the same pressure as 1 mole of a gas mixture in a 22.4 liter container, right? That's the volume of 1 mole of a gas. And since that value does not depend on identity, it doesn't matter if we have a case like at the extreme left, where we have 1.0 mole of nitrogen gas, pure nitrogen gas, would exert 1 atmosphere of pressure for 1 mole of gas. If we had a mixture of 0.4 moles of O2 and 0.6 moles of helium, that's a total of 1 mole of gaseous particles. There just happen to be two different types of components as opposed to the single component in the nitrogen example. So that overall pressure is going to be 1.0 atmospheres because the overall number of moles is 1.0 moles and the volume is that 22.4 liters. And we could go on and on. On the extreme right there, we see 3 gases that sum to 1 mole total and therefore 1 atmosphere. And we could go on to any number of gases if we wanted to extend this idea. So I think by now you've all got the point, so we won't belabor this any longer. All right, if we want to think about our most popular gaseous mixture, we could think about the composition of air. Air is a mixture of gases. As we said, it's overwhelmingly nitrogen. About 78.2% of the composition of air is due to nitrogen. Then about 21% due to oxygen. So we're up to I'm sorry, rather 99.2%. So about 0.8%, all these other gases, carbon dioxide, which is in pretty small amounts, although those small amounts have been climbing over the past decades, and that is causing us some concern. And then you've got argon, water vapor, all those minor components that give us a total partial pressure of 6 millimeters of mercury and a rough percentage of 0.8% to get that total composition of air. And I'm sure you've all become accustomed to these guides for solving problems. If we're going to talk about a guide to solving for partial pressure, first we're going to do what we normally do, write the equation for the sum of the partial pressures in this particular example. Second, we'll rearrange our equation to solve for the unknown pressure. Sometimes it's the total pressure. That tends to be the easiest case. More frequently, it's going to be one of the partial pressures that we'll be solving for. And then finally, we'll substitute the known pressures or solve a way to get the known pressures into the equation and calculate that unknown partial pressure. So a 3-stepper, not too bad. We've had 5-steppers, right? So this is going to be easy peasy for us. And because it's just a 3-stepper, we're going to toss you into it to solve it for yourself first. So instead of solving one together, it's time for our learning check where you're going to solve it on your own, and then we'll work through it together to make sure you got the correct answer. So in this learning check, we're told a scuba tank has a mixture of helium and oxygen gases at 7.00 atmospheres of pressure. If the partial pressure of oxygen gas is 1140 millimeters of mercury, what is the partial pressure of helium gas in the tank? So just pay careful attention to those units and we'll stop the video here. When you're ready to check your work, start back up and we'll see how you do. Okay, so step 1, as we said in our original setup, that step 1 involves writing the equation for partial pressure. So here we have the total pressure of gases in the container is going to be equal to, in this case, the two pressures of the individual gases that make up our mixture. So the partial pressure due to O2 plus the partial pressure due to helium. In step 2, we're going to rearrange the equation to solve for that unknown. So in this case, it's the helium we're looking for. So if we subtract the partial pressure of oxygen from both sides, we'll be left with the partial pressure due to helium. And then we can substitute in the partial pressure due to oxygen equals that total pressure of 1140 millimeters of mercury converted into atmospheres, right? If the total pressure in the tank is given in 7.00 atmospheres, then we should convert the pressure of O2 into atmospheres as well. We could also convert that total pressure of 7.00 atmospheres into a pressure in millimeters of mercury, but because atmosphere tends to be the chemist's unit for pressure, it's more logical to convert out of millimeters of mercury and into atmospheres rather than the other way around. Now that we have like units, we can move on to step 3 and substitute in those values to calculate the unknown. In this case, it's the partial pressure that's unknown. Sometimes it's the total pressure that's unknown. But here, the partial pressure due to helium is that total pressure of 7.00 atmospheres minus the 1.50 atmosphere pressure due to oxygen for a partial pressure due to helium of 5.50 atmospheres. So again, not terribly difficult, really not even as difficult as some of the things we've done in earlier sections of this chapter. So hopefully it's something that you were able to do all by yourself. Or maybe if you had made a mistake in the learning check, by working it together now, hopefully you see that it's not too terribly complicated. If, on the other hand, you find this terribly complicated, then certainly reach out to me. There's probably something that will help clarify things if we just get in touch and figure out where you're having your troubles. Now, because so many of you out there are interested in the health sciences or biology or something that deals with living systems, let's take a moment to apply these ideas of gases and partial pressures in particular to biological systems, in this case blood gases. So in the lungs, O2 enters the blood at the same time that CO2 is released, right? It's not a perfect system. You're not getting just oxygen in and just CO2 out, but you're getting higher amounts of oxygen in, higher amounts of CO2 being released out into the lungs. In the tissues, we have the O2 entering the cells, which release the CO2 into the blood. So we're oxygenating in the lungs and then bring that oxygen to the tissues and finally bring that CO2, the waste product of respiration, back to the lungs so that it can be released. So the processes governing this in the body are these partial pressures. In the human body or any animal that has lungs, as we humans do, you have the situation where the O2 flows into the tissues because that partial pressure of O2 is higher in the blood and lower in the tissues. So it follows a concentration gradient, a pressure gradient in this case. So CO2 flows out because of the same reason. The partial pressure of CO2 is higher in the tissues, lower in the blood, so there's a net movement of the CO2 from the area of a higher amount to the area of lower amount. And so this is all just nature obeying nature's laws, nothing special, no need for inputting a whole lot of energy to drive these processes. They're going with the flow. They're going the way that the concentration gradient would allow. And so we see here it's not huge pressure differences, but noticeable differences, more so with the oxygen than with the CO2, but again, just enough for the whole system to work well. If you're not able to get oxygenated blood to the tissues or the carbon dioxide waste products away from the tissues, then things get very dangerous very quickly, and that's why oftentimes people with compromised breathing abilities, something like chronic obstructive pulmonary disorder, they'll be placed on oxygen to increase that partial pressure of oxygen coming into the lungs and going to the tissues, and that seems to solve the problem if their own body is not capable of extracting the oxygen like a healthy person's lung system could do. And so to sum up this idea of partial pressures and this application of partial pressure to blood gases, we have table 7.8 here, which talks about partial pressures of gases during breathing. As you notice, the gas identity is listed, and then the difference between the air that's breathed in, the inspired air, the alveolar air, and the expired air. So the inspired air is richest in nitrogen, 594 millimeters of mercury partial pressure. The alveolar air is slightly less, and then the expired air, the air we breathe out, is lesser still. For oxygen, that inspired air is again the highest partial pressure of oxygen. The alveolar air is the lowest, and the air we breathe out is actually slightly more enriched than the alveolar air. And it's important that that oxygen is in our expired air, right? We're not perfectly efficient, and it's a good thing, because if we were perfectly efficient and we only breathed in oxygen and we only breathed out carbon dioxide, then we couldn't practice cardiopulmonary resuscitation. There'd be no oxygen in our breath to breathe into someone who's having trouble breathing or has passed out due to inadequate oxygen. So it's quite important, actually. It's life-saving that we have a significant amount of oxygen left in the air we breathe out, because that can therefore allow for oxygen to be breathed into someone who's having trouble breathing on his or her own. If you look at carbon dioxide, the air we breathe in is very, very low in carbon dioxide compared with the alveolar air and the air we breathe out. And then finally, water vapor. Likewise, the water vapor that's present in the atmospheric air that we breathe in is pretty low, but because of the fact that we're water-based beings, it's quite a bit higher in alveolar air and exactly the same amount in the air we breathe out. So we see in each case we get that total 760 millimeters of mercury, but the particular partial pressures can vary widely between the air we're breathing in, the air exchange at the alveolar air in the lungs, and then finally the air we breathe out. So hopefully that was exciting for those of you interested in the health professions. Even if you're not interested in the health professions, we're all biological beings, and if it weren't for all this stuff, we wouldn't be able to function. So hopefully you've got a vested interest in all of this, regardless of your professional goals. And that's it. That's chapter 7. It's taken a little while. There's lots of different sections, and hopefully you've stuck it through and listened to all the lecture audio and worked the problems with us, and have gone on to work additional problems where necessary, and certainly reached out to me if you do need help. But all in all, compared with chapter 6 that I know did bother some people, chapter 7's relatively straightforward, and hopefully a chapter that you didn't just do well in, but even enjoyed. If you like chapter 7, just wait till chapter 8. It's even more fun and exciting, and I look forward to working with you then.